Very good.
Well, hello, everyone, and welcome back to Sailor Academy's Introduction to Python. This is Unit 5. We have done 4 other reviews of units. If you have not taken the course yet, feel free to go to sailor.org's Python course, come back. I'll make sure there are links in the description below if you're coming out late. If you're live now, I'll put the links in the chat over there. Yeah, that's basically it. Let me just introduce you to Dr. Eric Sakk, who's going to take you through what we're about to do.
Awesome. Well, good morning, everyone. And
good morning.
What's that?
Oh, I was just saying good morning. If I'm being the class for you, I'm just
okay. Okay. All right. So we're going to talk about functions today, and I want to. I think what I'd like to do is maybe start not only to kind of go over functions, but also see if we can't maybe integrate some things from previous units, to sort of start to bring things together a little bit. So, the idea of a function in general, hopefully, I hope everybody's at least seen something in mathematics where if they showed you this type of notation where you have some function of x, like x squared or something like that. And basically, there's a rule that says if I give you any x, you take the number and multiply it by itself, and you get another number sort of from the function. So you're sort of like dropping an x in, and then you're getting an f of x out. And that's really pretty much what functions are, right? So here's your f of x. So for any function, you have an input. You've got the rule and what you want to compute, and then you get the output. So functions basically have inputs, they have outputs, and they perform some operation of some kind. The intent is to, and why you do that really is to, in some sense, if you're writing code for a living, what usually happens is like you find yourself writing chunks of code, and they end up reappearing several times in a program, and it just becomes more efficient at that point to sort of package all those commands up, all those instructions up into a little box that we call a function, and then you can call that function and you can give it a name, and you're allowed to do anything that you want with it. So in Python, or any programming language for the most part, there are built-in functions that the language kind of gives you in some sense as part of the package, I guess. And we've talked about that. And also, methods. We'll get to talk about methods also. Methods are basically functions defined within classes. And we're going to get to object-oriented programming. So you won't hear me talk too much about methods, but most of what I'm saying is going to hold true for methods as well, although the syntax will be a little bit different, because even last week we saw you type something, some variable name dot, and then you give the method name. So that's the syntax for methods is similar to functions, but not exactly the same. Anyway, there are built-in functions, and I think when we were doing lists, I may have shown you like the sum function, for instance. That's a function where you drop you don't have to drop, you drop a list in, for example, a numerical list, and it'll sum the values for you. So the input is the list, the output is the sum. And we'll get to the syntax and all, but those are built in. Those are part of, and then the beauty of programming is that you are the creator, right? You're the one who is giving the construct, so you can write any type of function that you want to. Those are user-defined functions. You get to define those. You're the expert. You're the one who comes along and says, I need an x squared function, or I need to do this, that, or the other thing. And then you throw the syntax together that allows you to do that. So it's very powerful. And let's see, so we'll pop over here again and do that. And I should be here, so I need to do that. So we'll come back over, and so the syntax for defining a function, let's just take that example we just did. The definition line, or the def line, is you specify the name of the function. Maybe I'll call a function x squared, for instance. So you have to give the function a name, and then there's going to be an input. And anything that's associated with the inputs, and functions don't always have to have inputs. There could be no inputs, but the syntax is in Python, you have to have a left parentheses and a right parentheses, and anything that you're sending to the function is placed within those parentheses, comma separated, and those are what the inputs to the function will be. And then you have to end it with a colon. So that's the syntax for a function call. What the plan is that I'm going to have a function. It's not going to be a very interesting function, but a function nonetheless, just to get the point across. We're going to take a number and square it, okay, and then we're going to return it, and we'll see how to do that. So the definition line is you use def. That's a reserved Python keyword. The word x squared doesn't exist in Python. If you try to use the word x squared, you get a syntax error because Python wouldn't recognize it until we define what it is. So I'm calling this function x squared, and then again, as I said before, the input is x, and just for the heck of it, I'll write it like this. This is not very efficient, but I'll do it this way. I'm going to take x and square it, and then what I'll do is I will return y. So if your function is going to have outputs, there must be a return statement that is going to send the answer, or answers, I mean, depending on how it gets defined, back from the function. So and the indentation is critical. It's key. You have to have indentation here to say what's in. So that should be no surprise. Python works by indentation. We've already learned if statements, while statements, for statements. They all kind of work in some sense the same way for their definitions. You define the programming structure that you want to use. You put a colon at the end, and then once you hit return, you indent everything that's associated with that particular programming structure. So again, not the most exciting function in the world, but maybe what we'll do is we'll set y equal to 2, and then we'll set z equal to the output. We could do it this way. Again, it depends on what your goal is. But so here I'm setting y equal to 2. Notice this we're back in main now, so I might as well even put a little comment here. Maybe I'll say something like this: main is here, something like that, because the function is separate and distinct from the main code. That's why you have the definition line. That's why everything is being defined outside of main in some sense. Main is just running this set of instructions, and I could go ahead and print, z at this point after it runs, and you would expect that after you square the number, that you'd see you'd see a 4 on the screen. And but the whole point of writing the function is that it can be called again and again and again. Maybe this time what I'll do is I'll do it with y equal to 3, and or maybe I'll do it with y equal to 4. So the idea is that you're planning on using the function over and over again, and really what you do is you've created your own personal command. Basically, you've created a new Python instruction, basically, and that's powerful. That's what makes programming so powerful, is you get to define your set of user-defined commands or instructions, if you want to think about it that way, and you can use it over and over and over again with different values. So you can see what happens is if we run this function, these instructions will execute, the values will be returned from the function, and you can use, I'm just using the variable basic z as a sink for the output, and so there's an assignment saying, basically it's saying whatever comes out of that function, drop it into the variable z, assign it to the variable z. So that's so every time this is being called, we're seeing different values be. That's interesting. Oh. I'm not squaring it. I'm not squaring anything. I'm actually raising it to a power.
Oh.
So there we go.
Just for the uninitiated, what would you want to explain what happened for the chat, not for me. Obviously, I 100% understand what happened.
So well, actually, but we'll do that in a second. Let's go back. So x squared is just x times x, right? X squared is x to the second power. So I'm taking x, and when I want to square something, I want to take a number and multiply it by itself. That's what the exponent does. X to the power 2 is x times x, and so I was thinking both ways at the same time, basically, because you could write it like this, which is x times x. Now, if we run it, we'll see the right answer, you know. But you could also do this if you wanted to use powers, x to the power 2, right? So you could say x squared like that as well. That would be a more faithful reproduction of what the equation I gave on the whiteboard was. Is that I'm trying to compute x squared, and that's x times x. So I kind of mixed those two together in my brain, and then I wrote x to the x power is what I was computing. So when I put in 2, it was 2 to the second power. When I was putting in 3, it was 3 to the third power, which is 27, and then 4 to the fourth power is 264, so on and so on and so on and so forth. So that's kind of how that works. So these are the right answers now. So I guess, first of all, for computing powers, you have a number of different ways to raise something to a power. In the math, we talk about the math module in the course, and so there's actually a POW function called POW, math.pow, and you can raise a number to a power using that. Or we can take x and raise it to the second power, or we can take x and multiply it by itself. So there's a number of different ways to achieve the same thing. But this is not, that is not x squared, okay? That's not x squared, that's x to the xth power, okay? So that's that. So here's the deal, and you should really think about this, because I find sometimes when teaching at the beginner level, students, the concept of a function is odd in some sense, and it shouldn't be. It's like when you're creating your own commands, and we're executing commands sequentially. So we start at line 11, then we execute line 12, then we execute line 13, then we execute line 14. So this is what's called sequential processing. Instructions are being executed one after the other, okay? And then you get this, and then you get this, and then this gets executed, and then this gets executed, and then this gets executed one after the other. That's the whole, idea behind sequential processing. Is you just, if there are no branching instructions, if there are no conditional instructions, like what we talked about, like with if statements and so forth, you're just going to go and execute. Remember, with if statements, there are sections of code that will not execute because you basically jump over them because a logical condition wasn't satisfied. So that's going back to the unit on conditional statements. But when it comes to just, if there are no conditional statements, then you're just going to execute instruction after instruction after instruction. And so x squared, the instruction x squared, the function, is like a Python instruction now. And so it's just going to execute. What's interesting is, just a little bit about how computer systems work is basically when you write when you execute this instruction, this is called calling the function. You call it, you make a function call. And what happens sequentially is that the processor, in some sense, leaves this code, comes up here, finds this function x squared, and then begins executing all the stuff that's in the function. And then when it sees the return statement, it knows to go right back here. It remembers basically that it was at instruction 12, line 12, and it knows to go to line 13 after the function executes. And that's a pretty amazing thing. You have to have something in your computer called a stack. It's called a stack-based architecture. But basically, the computer has to remember where it was in order to get back to the program. So the central processing unit literally jumps from here. It jumps up to this instruction, begins executing everything inside until it sees this return statement. And when it sees the return statement, it knows to go directly back to instruction on line 13. And, the print is a function, it does the same thing. The print is actually a, fairly, sophisticated function. You're dropping something in here and you're telling it to print it out to the screen. There's a lot that goes on in the background to do that. And then the CPU knows to return basically to line 14. And then you execute line 15 and jump up here to do all of this. And then you jump to the, and so sometimes in terms of program control, students get a little bit confused, about the order of execution, but it's completely sequential. And it's a good way to think about your program is once you've written the function, this really is like an instruction that gets executed in a sequential fashion, so that when you're done with this one, you get to the next instruction. And that's just the mechanics of how it works. So it should become very natural for you to be writing functions and ultimately methods as well, because what's going to happen, as I said, is you're going to have some operation that you want to perform, and you want to have it as one single instruction. It makes the code a lot more efficient, and it makes it neater, it makes it more readable. In the course, we talk a little bit later on, I think it's upwards towards Unit 10, just to distinguish between what's called object-oriented programming and procedural programming. When you're writing procedures, you're writing functions. Basically, you're thinking of your program in terms of small units, small chunks. And we'll talk more about this, like I said, when we get to Unit 10. But you're thinking about small chunks, and you create functions to execute those small chunks, and then they become reusable. You can use them over and over and over again. So functions are very, very useful. There's no way that you can become an excellent programmer without understanding how to write them. And they're not very complicated. I mean, look how fast I chucked this down on paper. Okay, so this was, very easy to do. So I'll take any questions about functions. I think I just want to make sure everybody understands the structure of a function call. There are inputs, there's code inside the function, and then values are returned. So that's how that works.
So we don't currently have any questions, but as usual, I'll just vamp and see if we get some. Mostly positive feedback. Our UX designer Ryan was in the chat saying functions are cool. So we have that as a comment for you. Okay. Do with that what you will.
They are.
Yeah, I'm just gonna talk for another couple seconds about mostly nothing, just to wait and see. Again, if you want, you can leave a question in the chat if you have a question, and also leave one down below. We'll get back to it if it's relevant, maybe in another video. But as of right now, that seems like enough delay time for people to have asked a question. So I'll just kick it back.
Okay, so what I'm going to do is I just thought maybe I'd throw out an example. I think that would be interesting, from a programming standpoint, but it requires a tiny bit of understanding of discrete math. So I'm going to spend about 5 minutes just teaching a tiny bit of discrete math for this example. But basically, there's this Greek letter, capital sigma, and sometimes you'll see stuff like this when you read about computer programs, like the sum from, you say sigma means you're going to sum something, you're going to start adding a bunch of stuff. And I want to bring this up because, like I said, this will help tie together, the basic for loop stuff that we were doing maybe last week or the week before. But if you're planning on summing some things and you've got a lot of terms, like 100 terms, and you wanted to write them all out, just like the for loop makes your code efficient for summing a bunch of items. The sigma sign does exactly the same thing on paper. It just makes it much. So if I said the sum from I equal 1, I'll take a small number, but make believe it was like 1,000,000, then I'm going to make it 3 though, because I'm not going to write down 1,000,000 elements. And maybe I'll say, I want to sum the elements from starting at I equals 0 to I equal 3. Well, this translates, unraveled, unpacked, unpackaged, that sigma sign means this. Whatever value of I is, you just sum it to the previous value. So this is very, very much like a for loop. In fact, I would say that if you ever see a sigma sign in something that you want to program up, you could almost conclude, like probably about 98.5% of the time, that you're going to use something like a for loop to implement that, like an equation, let's say. But I want to, you'll see where I'm going with this in a second. I just want to get through this notation. Or if I said something like this, the sum from I equals 0 to, and that's how it, to 3 of, let's say, I squared, right? I squared, then it's going to be 0 squared. By the way, this is, if anybody cares, that's 6, but I think you all can do that problem. So, and 1 squared plus 2 squared plus 3 squared, like this. You know, again, you can see how this notation could be helpful if I weren't just doing like the sum from 0 to 3. You know, if I were doing the sum from 0 to 1,000, this equation would get like ridiculously long. And so the reason that we pack it up in this is that it just makes it more efficient. You know, you don't want to write everything out like that. You know, that just gets too difficult, you know. Or if you have something like the sum, here's another one, like the sum equals 0 to 3 of, let's say, 2 to the ith power, let's say. So this is going to be like, I'll make it minus I, because we'll make it converge. Let's say 2 to the minus 0 plus 2 to the minus 1 plus 2 to the minus 2 plus 2 to the minus 3. So what's happening is that as the I varies from 0 to 3, you're counting by ones, basically. I'm telling you where to start counting. I'm telling you where to stop counting. And we're going to assume we're counting by ones unless there's other notation in there to indicate otherwise. So the sum basically tells us how to count. And then there's some term inside the summation sign, inside the sigma sign, that tells us the rule. Okay. So here the rule, anything to the 0th power is always 1. Anything to the minus 1 to the negative power is 1 over that. So that's like 1 over 2 to the first. This is like 1 over 2 squared. Just to remind you of negative powers, 1 over 2 cubed, which is 8. So you get a sum that looks like that. So notice, I mean, this doesn't look anything like this, but you have to kind of get used to working through the rule to generate the series of terms that you're going to sum together. But when you see something like this, okay, you automatically think for loop. I mean, you would program this up, or I'll say it in words because I'm going to assume everybody understands that material from the previous week. You do something like for I in range 4, right? Because you're going to count from 0 to 3. It has to be in range 4. And then you would just compute a partial sum of 2 to the minus I. And you would just sum those together, like I showed you how to do the running sum with the for loop. And I suppose what I'll do is I'll write the code for that. Let's just do one really quick. I guess rather than say it, let's just do it. And I'll write a little function, and I'll call it, I don't know what. In fact, I'll leave that one there. Let's say we'll define, you know, 2 to the I. And then I'll drop in a variable. I'll call it capital N. And I'll say 2 to the I or 2 to the N. I don't know. You know, let's do some. I'll call it 2 to the I or something like that. I don't know. And what I'll do is I'll set a sum equal to 0, and then we'll say for I in range. And you know, it's so funny. There's just so many things that would go into this. Like I'm going to send it n. I'm going to sum from 0 to 3. So if I do this, I want to actually add 1 to it. And you'll see, remember, because the range always counts to 1 less. But you know what's funny is I love it. Students are so accepting and sometimes because the in range, I haven't really even, it's there because it's actually a set operation. We haven't talked about sets. We're going to get to that next week. But you're all accepting of the fact that the range is going to give us some type of a set that is going to have the numbers counting from 0 to n, basically, which is what we want. So I could say like s plus equals 2 to the ith power. And if I do something like this really honest to goodness is the implementation of of that thing, that little animal that I wrote down over on the board over here. So if I do something like this, if I'm sharing this again, just to write it down again, to say for I equals 0, let's say to 3, what I'm doing is I'm going to send this variable n, which is the number, I'm going to send the number 3, and then we'll go ahead and add these partial terms together using a for loop. So this really will be, 1 plus 1 over 2 to the first power plus 1 over 2 to the second power. This is really just, I don't mean to freak anybody out with a little bit of discrete math, but this is the type of stuff that you're going to see when you're programming, so you might as well, I think this is a good thing to know. And I feel like it enables me to teach you functions using for loops, which we taught a couple of weeks ago. So I think this is a good example. And so we're going to take these terms, and sum them together in a for loop. So this is what we're doing, and this is actually the code that will implement this, if I can call this correctly. So what I'll do is I'll set I'll do it all in one line. I know before I was separating out variables and so forth, but what I'll do is so the assumption is that we're going to sum 2 to the I for that maximum value from 0 to 3. In this case, that's why I'm adding 1 to it, because I want to count from 0 to n. And remember, the range function is going to go 1 less than the number that I specify. So I'm specifying n plus 1. So notice I'm sending the number 3, which says count from 0 to 3. So my loop is being set up to count from 0 to 3. And then what I'm doing is I'm taking these partial sums, these partial terms. Remember how the for loop works is if we sum values, we're doing this every inning. So in the 0th inning, we have 2 to the 0. In the and we're not doing 2 to the I, by the way. We're going to do 2 ... minus I, just to be clear about that. Okay, that's what we're doing. That's what we said we were going to do over here when we sum these values together. It's 2 to the minus I. So to be faithful to what what we wrote there, and then the loop now is going to take these partial values, and every time we go through the next loop, we're going to add the 2 to the I term for I equals 0, and then the one for I equal 1, and then the next one to the partial sum for I equal 2, and then the next one for I equal 3. And then the last thing that we want to remember to do is after we have this value, we'll have the final sum after the loop runs, and we will return that value. Okay. So this is, the function is more like a contract. You're saying that these are the input values, and then I'm going to use these input values in this way to compute something, and then I promise to return this value s to you. So you have to expect that there's going to be an output, and whatever that output is, I'm going to just drop that in. I'm going to go ahead and print it. So if everything works okay, then what I've done is I've summed 1 plus a half, which is 1.5, plus a quarter, which is 0.25, and that's 1.75. And then you go ahead and get 1 to the 1 over 8, and now you're at 0.125, and you add that, and you get 1.875. So this is the right answer. It seems to be that. And you could check this on a calculator. You can test it. You could easily go into a calculator and add 1 plus a half plus a fourth plus an eighth, and demonstrate to yourself that this really gives you, the right answer. But the main reason I'm choosing examples like this today is because I want to immediately begin applying concepts from previous units in a way that sort of brings everything together. After this unit, we kind of go off on a number of different, I would say, more sophisticated aspects of Python, but I think units 1 through 5 you'll find are very consistent with the way most programming language courses work. There's always a discussion about loops. There's always a discussion about conditionals. There's always a discussion about functions. And so I think this is a very sensible point, like halfway through the course, to try and tie everything together. And what you need to have the ability to do is to be able to take these structures and plop them into functions, and be able to sort of play around with them and feel very comfortable making function calls to compute stuff. So this is just like I said, it's just I'm summing, that's what the function is doing. I'm summing 2 to the th power in this case. Okay. Any questions about that? So that, yeah.
We did have a question here from Enrique about recursive functions.
Yeah, we don't talk a lot about recursion in the course, and
is it so I'll just paraphrase. I don't want to cut you off, sorry, but so I guess, is it different in Python than in other coding languages?
I think Python affords one a certain measure of convenience that I think other languages might not when it comes to certain recursive structures, because you can write some really interesting return statements, I think, with Python. So, for instance, just as an example, if you were going to make the attempt to make a recursive call, for like a linear search through an array, and the way that you sort of break the problem up into its recursive pieces, it's very convenient to like integrate slicing, list slicing into a solution like that. And you can't, in languages like maybe C or Java, you wouldn't have that, albeit it's possible, and of course you can write code to do it. I think with Python, the code becomes a lot more compact, and much more reflective because of lists and slicing. It becomes much more reflective of what the recursion is actually doing when it comes to sort of breaking a larger problem down into a bunch of smaller problems. But I think outside of the syntax, I mean, recursion works exactly the same way, because recursion is recursion. You have to have a stack-based architecture. You have to have a base case so that you don't make an infinite number of recursive calls, and so all that pretty much stays the same. But I would say it's interesting to compare like the implementation, for instance, of like a binary search, how you would do that in a Java or a C versus a Python. That I think Python actually gives a much more elegant looking solution, simply because of how lists and slicing work. It's much nicer, I think, anyway. But it works the same way. So I mean, we could try a simple, like a Fibonacci or something like that. If you wanted to do like an f of n is equal to an f of n minus 1 plus f of n minus 2. This is a typical type of introductory recursive type of an equation. And like so this would work exactly the same way. You'd end up with like a return, just as an example, you'd end up with a return statement that would be like, if you called the function Fibo or Fibonacci, just to make it sort of Fibo, it would work almost exactly the same way, as other, languages. But the one-to-one translation, I think, if you had your function Fibo that was adding together, this is what a return statement would look like in Python. So these types of single variable recursions, on like recursive equations or difference equations, I don't think there's much difference between Python and many other languages. But I think when you get to more, search types of questions and sorting types of questions, you would find that the implementation is a little bit more elegant, I think, than what you would see for typical languages that don't give the list slicing. So I hope I'm answering that question.
I hope so. Yeah, I think I saw a thank you, I think, in the chat. So I think we might have got it. So I think we need to probably move on to the next bit.
Okay, sorry.
Yeah. No, I'm the one that derailed you. Don't worry about it.
No, it's okay. I'm just thinking, in the back of my mind, I'm thinking whether or not I'm going to stay focused on this. I was almost tempted to like quickly write a recursive program, but I'm trying to stick to what's in the course. Like, it's an introductory programming course, and my we didn't go into recursion for that introductory course, but there's a place for it in introductory courses, and it just, for some reason, that didn't, we had enough, I think, enough material with the 10 units to not do that. And even as that question comes up now, I'm thinking, that might be an interesting addition to this unit. But I want to stay focused on what's in the course, because I was almost tempted to write like a recursive program, but we don't go into it in the course. So it's like,
right. Yeah, maybe we'll come back to it,
Okay. All right. Anyway, so let's continue with this summation business, because I wanted to show you something that I thought was kind of interesting. Or would be interesting if we understand the summation notation. Now, do not freak out on me here, okay? I'm gonna write this out. Okay, I'm gonna write this out as the summation. Let's say from I equals 0. I'll choose 3 again because it's finite math. This is just discrete math. It's just basically addition, subtraction, and maybe raising things to a power. I got to show you one little function. And speaking of recursion, by the way, I'm going to show you the factorial function, and I think we do talk about in the course, because I think I give a loop example that uses the factorial operation. But n factorial is just start at the value n and then start multiplying numbers all the way down to 1. So 3 factorial is equal to 3 times 2 times 1, and 4 factorial is equal to, and you could, I actually think I give a question. There's a quiz question I give on factorials. But again, it's done iteratively. It's not done recursively, because you could do it recursively as well. But anyway, so that's all. If I say something factorial, you just basically take the product of all the numbers up to that number. And again, you could easily, I'm going to assume that everybody could write a loop to do this, because this would be something that you would have learned in the loop section of the course when we talked about program control. The only thing you got to remember is, so 1 factorial is equal to 1. 2 factorial is equal to 2 times 1, which is 2. And the only thing you got to remember is that 0 factorial is defined as 1. So the factorial function is defined over integers, non-negative integers. And it's generalizable. I'm not going to go into, there's something called a gamma function, which sort of takes this discrete version and makes it continuous. And there's something from that can be derived to compute something called Stirling's approximation, because this n factorial really grows fast. It blows up like really fast. And so these numbers get large really quick. And so there comes a point where it doesn't become sensible to do it with integer operations anymore. You want to use floating point operations that approximate what that big number will be. And that comes out of something called Stirling's approximation. But the point is that just take my word for it. This is a good definition. So 0 factorial is defined as 1. And so 1 factorial is 1, 2 factorial is 2, 3 factorial is 6. 4 factorial is 24, 5 factorial is 5 times 3 times 4, 120, so on and so forth. And so the reason I'm showing this is because I'm going to show you a formula. And what we're going to try and do is we're going to try to build a function the time we have left together. The function is this. I'm going to take -1. I'm going to raise it to the ith power. And then what I'm going to do, I'm going to call this a function. I'm going to call it f of x, which means I can drop x's into this. And it's going to I can drop a whole bunch of x's, any x I want to, and I'm going to get an answer out. And I'm going to raise x to the 2ith power and divide that by I factorial. And so the first thing that we want to do is, is evaluate each term. This looks really nasty if you haven't seen stuff like this before, but I don't want you to be afraid of stuff like this. It's not hard. It's just discrete math where you're summing a bunch of simple terms together depending on what the value of I is. In this case, we're actually dropping an x in as if this were a function. So if I do the 0th term, set I equal to 0, and just anywhere you see an I, you plug in I equals 0. So that's I to the 2 times 0. And that's over 0 factorial, okay? And then we'll take -1, because we're programmers now. You shouldn't shy away from stuff like this. It's not hard to do. And honestly, if you do program a lot, you're going to see this stuff quite a bit, you know, as you get more sophisticated. Plus, so why don't we do a little computer science together, just a tiny bit, okay? Plus this squared, when I is 2, it's x to the 2 times 2 divided by 2 factorial. And then if I is equal to 3, then that's the I equal 3 term. It's going to be -1. Wherever you see an I now, for this term, you put a 3. And then it's going to be 2 times I, which is 3. And it's going to be over I factorial, which is 3. Okay? And I'm going to tell you something right now. There's something called a Taylor series, and if you ever press a function on your calculator, maybe you were taking like trigonometry in high school, and you had to compute like a cosine function, and I'm sure nobody ever asked the question, I wonder how they compute that, because the cosine is just a theoretical object. You know, it's just if you have a triangle, it's just the ratio of, you know, this distance. If you have at an angle theta. The Greek letter theta is what you used to use for angles. Go back to high school trigonometry. You know, if you take x and you have a radius r, it's just x divided by r. That's what the cosine is. And so you have to have what's called a numerical method for computing this. You can't and also it's a transcendental function. It's like it doesn't, in principle, you know, a lot of values that you compute for the cosine function, theoretically the numbers go on forever, they never end. But computers are discrete, right? So you can only process an approximation to that number. Well, I'm going to tell you that this function right here, this f of x, is approximately equal to the cosine of x. And I'll evaluate this in a second, but you can see this term, anything to the 0th power is always 1. So x to the 0, this whole term, -1 to the 0 is 1, x to the 0 is 1, 0, this is 1. So that this nasty looking thing where I'm taking this number and raising it all to all these powers, it's just a 1. In the next term, -1 to the 1st power is -1. So you'll actually get -1 times x squared over 2 factorial. And then you'll get, the next term is -1 squared. -1 times -1 is +1. This is x to the 4th. I'm sorry, this should be 2 times this, 2 times that, and 2 times that. Sorry about that. So this is going to be over 2 factorial. And then what's going to happen is the next term is going to be x squared over 2 factorial. And then here you'll get negative for the next one. This is the x squared term. Now you have an x to the 4th term plus x to the 4th over 4 factorial. And then you'll get minus for this term, -1x to the 6th over 6 factorial. If you work this out, if you work this term out, okay, what's going to happen is you're going to oopsie daisy, put that in there like that. What's going to happen is this is what you'll end up with. You're going to end up with f of x is equal to, and I encourage you to do this. I really do. This is, it's, if you can look it up, it's called Taylor series. I'll just do 3 terms. And it's a Taylor series for the cosine function. I'll write this again, x to the 2i. So again, this could look like a complicated animal. And I'll put this in parentheses. So the point is, though, when you get done with it, it looks like this: 1 minus x squared on 2. So it's called an alternating series with even powers. It alternates plus minus, plus minus, plus minus, okay, over 4 factorial plus, I'm sorry, minus x to the 6 over 6 factorial. And like I said, I encourage you to look this up, because my claim is that if you take an infinite number of terms, that this will be equal, if you go dot, dot, dot and went on forever, this would be equal to the cosine of x, okay? So what I'm going to do now in the last few minutes that we have is we're going to write a program. We're going to write a function to compute this. And then I'm going to convince you that it's actually equal to this. And I'm going to show you how I'm going to do that, okay? What we'll do is we'll define a function, and I'll call it cos approx. And I'll send in a value x. Sorry, I'll send in a value x. And then I'll send in the number of terms I want to compute in my sum. On the whiteboard, I used 3 terms from 0 to 3. But now what I'm going to do is I'm going to create a sum, set s equal to 0, partial sum. We'll have a for loop. And again, it's the same game. We're going to have I in range, let's say n plus 1. Okay, we'll take it out to, that value again. So nothing changes in this code right here. It's exactly like what we did for the 2 to the I. And then we'll have like s plus equals, and we're going to have this term. Okay, now in order to make this work, there's a point where we introduce the math module, and I think it's somewhere around it's right about now. It's right about now that you've seen the import command where we import a module where we could do some math, and then I introduce raising numbers to powers, trigonometric functions, and so forth, and factorials. So in this case, we can write something like this. We could say maybe like this: -1 to the ith power. Okay, that's the first term. The second term, now we multiply by x star star, let's say 2 times I, like that. Okay, so that's the second term in the summation. If we come back over here, I'm trying to implement this, and so you have to get the first term -1 to the ith power, and then you have to get the x to the 2ith power, and then we have to divide that by the factorial of 2i. Okay, so we need 3 terms in that summation, okay, in that partial sum. And so if you come back over here, I've got the first term -1 to the ith power. I've got x raised to the 2i, and then I'm going to divide this by, watch this in slow motion now, math dot. So this is a method that I'm calling within the math module. It's the factorial method, and I'm gonna put 2i in here as well. Okay, and then what I'm going to do is I'm going to return this, let's say. Okay, and get this guy out of here. Return s. Okay, and so what I'm going to do now is I'm going to call cosine approximation, and oopsie daisy. That's replit. That wasn't me. And I'm going to call these functions. I'm going to call the function with these values, and I'm going to I'll set x equal to, some special angle. We'll set it equal to 0, and the cosine of 0 degrees is always going to be 1. So that's an easy check. And maybe we'll take like 4 terms. We'll let n equal 4 in this, or we'll use n equal 3. So we'll use n equal 3, and I'm going to call this function with these values, and you'll see over here the answer that gets printed out is 1. So at least for x equals 0, the cosine of 0 degrees, we're getting an answer of 1. So but I think the most important question is, if I used a different x, like maybe if I use like your special angles, if you remember, 45 degrees in radians, again, go back to basic trigonometry, is pi divided by 4. So math.pi, there's actually a pi in the math module, pi divided by 4 is 45 degrees. So if we go ahead and run this, then we get something that looks like 0.707. That's 1 over the square root of 2. That if you go back, like I said, and review, you'll remember that the cosine of 40, there were special angles that they wanted you to remember, and one of them was the cosine of 45 degrees. And the cosine of 45 degrees is 1 over the square root of 2, which is 0.707. So it looks like this is approximating potentially the cosine of an angle. Now watch this though. This is the most important thing, is that if we really, really wanted to know if we were approximating it, you'd want to compare there's an ABS function that's built in Python, which is the absolute value. The cosine of x minus, watch this in slow motion now, the cosine of x minus our approximation. We want to see if we have a good approximation going on, okay? So what we're going to do is we're going to compute the difference between, oopsie daisy, math.cosine, okay? So we're applying the math module to compute the cosine of x. And then we're going to say, compare this value, the value that you would get from your calculator, compare it to this approximation, this what's called a series approximation or a Taylor series approximation to the cosine of x. And we drop this x in and we're going to compare them. And we're going to see what happens. So what did I do wrong here? Unexpected end of file. Oh, did I do something down here? What's the matter here? No, that's good. Oh, that is the difference between that and that. Sorry. There we go.
I could have told you that.
Yeah, no. I could have told me that. Okay. So, you know what it is? It's that Replit is a little frustrating because it tries to finish lines for you, and sometimes it'll put in stuff there that you never meant to do, and it's whatever. Anyway, but watch this now. So now the difference between the cosine function that the math module computes and the one that we just constructed through this series approximation, we're good to about 6 decimal places. They're actually very, very close. If we take more terms, if I go ahead and take more terms, like let's go ahead and take 10 terms now. So that summation would go out over 10 partial terms, 10 terms, which would give us a better approximation. Let's go ahead and see what happens here. Now we get a better approximation out to 16 decimal places. So it looks like this function that we've written actually approximates the cosine function. And again, I don't need to go into all the details of where that equation comes from. If you ever taken a calculus course, this usually gets brought up in like a Calc 1 or a Calc 2 type of, when you talk about what are called infinite series. But that's, we don't have to go down that path because we're cutting our series off because we do discrete math. Computers only compute a discrete number of terms. So the reason I'm showing you this application, because I think it's a really good aspect of numerical methods, of how a computer computes functions using these finite series, basically. That's how it does it. May not necessarily use this one. There are more efficient implementations, but let's say for trigonometric functions or cosine functions. But the general idea is that you've got a host of functions either on your calculator or within the math module. And the question is, how does a computer compute those things? They pretty much use these series kinds of solutions to compute, to approximate pi, to do anything really. And so this is one example of approximating the cosine function. And so then you can test whether or not it's a good approximation or a bad approximation. How do you do that? Well, you use Python's cosine function, you compare it to your cosine function, compute the absolute value of the difference, take the difference between those two answers, take their absolute value, and then see if that's getting smaller as you take more and more terms. So hopefully these two examples are tying together stuff that we did with loops and for loops and computing partial sums and that summing function we were talking about, and sort of integrating those now into callable functions that you could use over and over and over again. I think if you walk out of today's lesson, understanding all of this, you'll be well primed for the second 5 units. But this is really, again, there's a difference, you'll hear me say this over and over and again, there's a difference between memorizing syntax and applying it to write actual programs that solve problems. In this case, we're applying syntax, and so I'm talking to you as if you're experts with for loops now, and experts, on various modules that we've introduced within the course. And now we're trying to apply them to, in this case, make a certain kind of a computation. So, I hope that ties, this aspect ties together really the first 5 units of what's been done in the course, so that we can kind of take a breather and then go, oh, okay, well, I put all this together into this example. Now let's move on to the next units to do even more interesting things. So that's just an example I thought of. I thought maybe it might be helpful to see, this stuff integrated with previous material. That's about all I wanted to say for today.
Oh, well, that's great. I just, I want to before I reiterate to everyone that, this is part of the Python courses, Unit 5, you should definitely go back. We have other videos that are recaps of the unit, but you should go to Saylor.org, CS 105, and start learning Python. Replit is the program that you are using to show everyone how to do it. But while we wait to see if there's some more questions, I just want to ask you, because you seem crazy. So I was thinking while you were talking about it, I can do 3.14159 of pi. How much pi do you know while we wait?
Oh no, I never did that exercise. I never really memorized a lot of those digits. I suppose I should, but I just never did. It was never my thing for some reason. Some people like, you get to, I can remember pi. All right, whatever, okay.
Well, it's just one of those things where like you're just like, everyone knows the square root of whatever is whatever, and I'm like, you must know what pi is. So do I know more pi integers than you? Because I feel like
you know more pi digits than me. You do.
Great. All right. So everyone, we'll be back here next week, March 10th, 9:30 a.m. Eastern time. Again, check the comments below. I'll put it in the chat again. This is for our Python course, and definitely, if you haven't caught up with us, catch up with us. We've done 4 other of these videos that are all related to the course on Saylor.org. So catch up. Leave a comment on an old video. I'll look back and see if we can answer that question maybe in a newer video. And as always, Dr. Eric Sakk, you're the best. You teach it like nobody else. So thank you, everyone, and we'll see you next week.